Hello viewers and subscribers of this channel. In this video I will teach you how to implement the recursive least squares method in Python. Okay, but before we start, let us briefly explain the importance of the recursive least squares method. The recursive least squares method is extremely important mainly because it serves as the basis for the development of a large number of algorithms. For example, it serves as the basis for development of adaptive control, system identification, state estimation, and machine learning algorithms. In this video, I will teach you how to implement the recursive least squares method in Python in disciplined manner. When I say in a disciplined manner, I mean the following. The code that I will explain and that I will teach you how to write will be easy to understand, will be properly commented, and it will be reusable. Reusable is a very important property of the code, and you really need to learn how to write a code that other people can use or that other people can take over and start to develop a more complex code from the code that you wrote. Basically, I will teach you how to write a class together with its methods and functions that implement the recursive least squares method. But before I start, I would like to mention a few important things. First of all, those of you who follow my work or who are my subscribers know by now that I always create a post that nicely summarizes everything that I will explain in this video. And here is the post. This post contains equations and Python codes, together with explanations. A link to this post is given in the description below. Secondly, it took me a significant amount of time, energy, and effort to create this video and this post. Consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Here are the equations that mathematically describe the recursive least squares method, and we will implement these equations in this video. If you want to learn how to derive these equations, I suggest you that you go to my website. You can click over here on Kalman filter link, and you can click over here. The post name is Introduction to Kalman filter, derivation of the recursive least squares method. So if you click here, you can find a complete derivation of the recursive least squares method, and this derivation basically assumes that you don't know anything about the recursive least squares method. That is, I derived the least squares method from scratch. Okay, so let's go back to our equations and let us analyze these equations. We basically have three equations that we need to implement. The first equation is the gain matrix update equation. The second one updates the estimate, and the third one, the one over here, is the equation that describes how the covariance matrix, or better to say, estimation error covariance matrix, is propagated over a discrete time period. Let us now dive deeper and let us try to understand the true nature of these equations. The proper understanding of these equations is crucial for proper implementation of the recursive least squares method in Python. The first thing that we need to keep in mind is that these are discrete time equations. This index k over here is a discrete time step, and it goes from 0, 1, 2, 3, etc. Then, we assume that at every discrete time instant k, we obtain a measurement sample denoted by y1, y2, y3, etc. That is, yi is a discrete time measurement obtained at k is equal to I. At the initial time step k is equal to 0, the user of this method or the person using the code should first select an initial value of our estimate, and this initial value is denoted x0 hat, and he or she needs to select an initial value of the covariance matrix. When I say covariance matrix, I actually mean an estimation error covariance matrix. Just keep in mind this thing while watching this video. And this value, this initial value of the covariance matrix, is denoted by P0. So at the initial time step k is equal to 0, we initialize our algorithm with x0 hat and with P0. Now, k becomes 1, the first time sample. At this time sample, we obtain the measurement y1. And on the basis of this measurement y1, we need to somehow update our initial estimate and our initial covariance matrix. So how to do that? The first step is to update the gain matrix. The gain matrix is this matrix kk. So we have k1 is equal to p0, and the p0 is an initial guess of the covariance matrix, and then we have this matrix over here, C1 transposed. C matrix is our measurement matrix. In the recursive least squares method, we assume the following measurement model. Yk is equal to ck multiplying x. X is the vector that we want to estimate. That is the vector of parameters that we want to estimate, plus vk, where vk is our measurement noise. And this matrix ck is our measurement matrix. Then, here in the parentheses, we have the matrix R1. Here we assume that we know both the C1 matrices and R1 matrices. R1 matrix is nothing less than the covariance matrix of our noise term at the time instant k is equal to 1, and we assume that we know that covariance. We can, for example, estimate the noise covariance matrices before the actual estimation is being performed. And we also know the term over here, since we know C1, we know P0, and of course we know C1 transpose. And then we invert this matrix. Now that we have computed our gain matrix, we can update the estimate. So we can write x1 hat is equal to x0 hat, and we know x0 hat plus the previously computed k1 gain matrix multiplying our sample minus c1 times x0 hat. So we know the terms on the right hand side, and consequently we can compute or update our estimate. The third step is to propagate the estimation error covariance matrix, and we will use this equation. We can write P1 is equal to I minus K1, and we have computed K1 in the first step, multiplying C1, we know C1, multiplying P0. So we know all the terms on the right hand side, and we can compute P1. And that's it. These three steps are being recursively performed. So basically we have a recursion in K. We start with K is equal to 0, then we go K1, K2, etc. At every time step K, we obtain the measurement, we update the gain matrix, we update the estimate, and we propagate the covariance matrix. Before we proceed with coding, we need to see what needs to be memorized and what needs to be computed during the code execution. First of all, the input should be x0 hat, p0, The covariance matrices of the measurement noise R1, R2, R3, etc. In this video and in the post I wrote, I assume that all these matrices are constant. However, in practice, they might not be constant. However, this is just a simplification in order to make this video as short as possible. And of course, we need to basically have in advance our measurement matrices C1, C2, C3, etc. Again, in this video, I assume that all the C matrices are time invariant. That is, I assume that their C's equal to C and they're constant. Okay, so these are our inputs. And let's see what needs to be memorized from one step to another. Obviously, we always need to memorize this matrix pk. That's obvious. Then we also need to memorize our estimate because we are updating the estimates. And basically these two quantities are the only quantities that need to be memorized from one step to another. However, I will write a code that will not only memorize these two quantities, but that will also memorize this term over here, that will also memorize our estimation error, and that will also memorize this correction term over here. This is done in order to track the convergence of the algorithm and in order to properly understand the algorithm behavior. And it's always a good practice while you're developing a code to write a part of the code that can be used to kind of investigate or debug if something goes wrong. Okay, so let us proceed with Python implementation. As you can see, I'm using Spider Python environment. I like the Spider environment since it reminds me of MATLAB because you can simply select a piece of code and you can simply evaluate it. Okay, so I will write a class called recursive least squares that will implement the recursive least squares method. And that's the power of Python. It's very easy to write a class and its functions and methods that implement a complex algorithm. You don't need to worry about memory allocation. You don't need to worry about pointers. You don't need to erase the memory after your destructor is being called. Everything is much more easier in Python compared to C++. That's one of the reasons why the Python is so attractive and why the Python is so widely used. The first step is to initialize all the variables that are being stored by our objects. And for that purpose, we will write this function over here, def init, and the input arguments are x0, p0, and r. x0 is the initial guess of our estimate, that's x0. P0 is P0, and R is the covariance matrix of the measurement noise. We initialize the values over here, and then I need to keep track of another variable, and that's my variable k. That's the discrete time instant over here. I need to keep a track of this discrete time instant, and I need to update this discrete time instant, or better to say to increment it after every prediction step. I will explain this later in the video. Then I need to keep a list of my estimates, x hat k, and this list over here will keep the track of these estimates, and initially I need to append my estimates with initial guess x0. Then I need to store my estimation error covariance matrices, and over here I'm basically updating or appending my estimation error covariance matrix with initial value denoted by P0. Then I need to keep track of my covariance matrices. This list over here is used to track the covariance matrices, and I need to keep track of the corrections, or better to say of my prediction errors. So these correction terms are actually basically equal to the term over here. So this will be EK. This is my correction term. If the correction term is equal to 0, then this update over here is equal to 0, and x hat k is equal to its previous value. Then I wrote a function called predict, and this function basically implements all three steps. Now what happens? First, I compute my gain matrix. I compute this gain matrix by defining another matrix called LK. So LK is equal to RK plus CK PK minus 1 multiplying CK transpose. So this is my LK, and I can simply write that my KK is equal to PK minus 1 CK transpose multiplying LK inverse. This is the formula I implemented over here. And here is my gain matrix. Notice here that I'm using the NumPy library, and I'm basically multiplying the matrices by using the math.mol function. Similarly, I'm also inverting matrices, and I'm using numpy.linearalgebra inverse function. Now we need to compute the corrections, because we need to compute the gain matrices. So first we compute this part over here, and these are our corrections. Then we multiply the correction with the gain matrix, and we add the last term to our previous estimate, and we obtain estimates. And finally, we propagate the estimation error covariance matrix. Basically, we implement this equation over here and compute the covariance matrix. And after we have performed all these computations, we update the lists. We update the lists storing estimates. We update the list storing the estimation error covariance matrix. We update the list storing gain matrices, and we update the list storing the errors. And finally, and this is a very crucial step, we update our time step. So what happens after this step? K is being increased. Now what I skipped to explain is the following. The input arguments of this function predict are measurement value, that's our yk, and our C matrix. So after I create my object, I can call the function that object dot predict. I specify the measurement value, that is, I specify yk term over here, and I specify another variable, and that's my C matrix, as arguments. And this function will perform these three steps, update all the lists storing the variables, and increment the time instant k. And I can do that in a for loop or in a while loop. So before I write a driver code for this class, and before I explain you how this class can be used in practice, let us consider this example that we will analyze and that we will simulate in this video. So over here I'm considering a vehicle moving from some starting position y0 with some initial velocity denoted by v0 and with an acceleration denoted by a. And our goal is to estimate initial position, initial velocity, and acceleration by only measuring position values y of t, where t of course is time. And from the basic equations of kinematics, we know that the position, velocity, and acceleration can be related by this equation over here. So the position at the time instant t is equal to initial position plus v0 times time plus 1/2 acceleration times time squared. Next, we assume that we are able to measure the position at a discrete time instance t is equal to 0, delta t, 2 delta t, 3 delta t, etc., where delta t is the sampling period of the sensor. We can simply represent y of k delta t by yk. And from this equation, we obtain our measurement equation. The measurement equation takes this form, where this part over here is our C matrix, this is our vector of parameters x, and this is our measurement noise. And of course, C depends on time, so we have a CK over here. So the measurement model is yk is equal to ck times x plus vk. And that's the standard model, the standard measurement model for applying the recursive least squares method. So the goal of the recursive least squares method is to estimate the vector x recursively on the basis of the sequentially obtained data y0, y1, and y2. That is, we want to estimate initial position, initial velocity, and acceleration by measuring the position at the time instance 0, 1, 2, 3, etc. Okay, so let us go back to our code and let us use the class we wrote. But before we use the class we wrote and before we explain how to estimate the parameter x, we need to perform a few steps. So the first step is to make sure that the file storing this class is properly located, and that is that Python can find this class. So over here, I will click on my C, on codes, and here's my folder. And I will click select folder. So this folder contained recursive least squares implementation, and you can see it over here that the file is located in this folder. So just make sure if you're using the Spider Python environment that the path over here matches the path over here. Okay, so let us go to our driver code. The first step is to import the libraries. We need to import NumPy libraries, and we need to import from matplotlib.pyplot, we need to import plot. And of course, we need to import our class. Okay, now let us simulate our system. Here I'm assuming the initial position of 10, acceleration of 5, and initial velocity of -2. That is, if you go back to our model, I assume the true values of the entries of the parameter vector. That is, I'm assuming the true values that we want to estimate. Here I'm assuming the noise standard deviation of 1. Then I'm selecting the simulation time step. So I'm starting from 0 until 15 seconds, and in between I have 2000 samples. Then I create an empty vector called position, and I need to fill in this vector of positions by simulating my model. That is, by simulating the model that you can see over here in a for loop. So let us simulate that model. And we can see that basically we obtain a vector of positions. So we can type positions, or better to say position without, and here are the results. Now, let us add the measurement noise to the position. So I will simply select this thing to obtain the measurement noise. So let's see our measurement noise. Here's our measurement noise. And let us plot the results. And here are the results. I can basically see them over here. Or you can go back and you can basically search for your folder over here, and you can see over here a PNG file. So what we can see over here, this is the ideal position and this is the observed position, and the red position is the noisy position that we will use to test our estimation algorithm. The next step is to select the initial guess of x0 and also to select our initial value of the covariance matrix. Here I'm assuming that I don't have any a priori knowledge related to my estimate. That is, I don't know anything about the parameter vector that I want to estimate Consequently, I will assume that x0 is completely random. So this is my x0, completely random, and I will select a relatively large value of my covariance matrix. That means that I'm assuming that I don't know anything about the parameter vector that I want to estimate. If you have a perfect knowledge about the values of the vector that you want to estimate, then you will simply assume here 0 times identity matrix. However, I'm assuming that I don't have any a priori knowledge. Consequently, I'm assuming 100 times an identity matrix. And finally, I need to select my measurement noise covariance matrix. Notice here, while selecting the measurement noise covariance matrix, I selected this value, scalar value multiplying the identity matrix to be 0.5. And here I'm deliberately introducing model uncertainties. Because if you see over here, the noise standard deviation is equal to 1. And consequently, if I have a perfect knowledge of my noise, then here the parameter should be equal to 1. However, in practice, you don't have perfect knowledge about statistics of your noise. Consequently, I try to simulate this or to emulate this situation in this code by deliberately making this error. And I want to see how my recursive least squares method will behave in this case. Okay, so let us create a recursive least squares object. We can do that by simply evaluating this code line. But before evaluating this code line, I will erase everything since I think that I run the whole code a few times. So I just want to make sure that I'm starting from scratch. So I will remove all the variables and I will execute my code from the beginning until this code line 49. Okay, and then I can basically type RLS to see what happens. Of course, nothing happens because we cannot access all the methods and all the variables stored in our object like this. We have to write something like RLS dot, for example, x0 to see x0. Okay, that's perfect. How about, let's see, RLS dot, let's see, estimation error covariance matrices. Let's see what will happen if you type something like this. Perfect. This is our stored covariance matrix. Okay. And the next step is to recursively call these three equations. As I explained previously, we can write a for loop, and in every basically iteration of this for loop, we can call this function predict by specifying as the first argument of that function the measurement. In our case, this is position noisy and the index is j, and I'm also specifying my measurement matrix. So we can simulate online behavior of the recursive least squares method by simulating or by calling these code lines. And let us plot the results. Let us see the performance of the recursive least squares method. The first step is to extract our estimates. Because if you see over here, if you type something like this, rls.estimates, basically you will have a list. every entry of this list will be a vector with 3 entries. So if you want to extract the first estimate, you will need to write something like this. J will be index for k, and 0 will be index for the entry that you want to extract. So let us see, did we basically correctly extract our estimates? Yes, they are correctly extracted. And over here, I'm just creating vectors out of these estimates, or better to say the vectors out of our true values of estimates, that is, the values that I assumed over here. I need to have a baseline in order to compare the estimation performance of the recursive least squares method with the true values that are assumed at the beginning of this code. So I'm simply forming vectors that will consist of constant values of my true parameters. Let's execute these code lines, and finally I can plot the results. And here are the results. Okay, so I will go back and open this file over here that you can see over here. So what happens over here? This is the convergence of the first estimate. That is the estimate of the position. The red line is the true value of the position. As you can see over here, this value is equal to 10. And it's constant. And you can see how my recursive least squares estimate converges relatively quickly to the true value. The second graph shows the convergence of the second parameter, that is the convergence of my velocity. The true value of velocity is basically -2, and you can see over here that my recursive least squares method and the second estimate converge to -2. And similarly, you can see that the parameter, the third parameter, that is the third estimate, converges to the true value of acceleration. And going back to our code, the true value of acceleration is 5. And looking at our graph, we can see relatively fast convergence. We can say that approximately after 250 time samples k, our recursive least squares method converges. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please subscribe and support my channel. Thank you very much and have a nice day.